we have defined a tensor as a linear transformation from one vector space to another. We now consider properties of tensors. A property is a derived attribute whose definition, that with a basis on the definition of tensors. These are derived attributes that have the definition of tensors as their basis. We'll often need to consult the basic definitions to establish the tensor characteristic of any object of concern. So we will never stop saying a linear transformation from one vector to another, from one vector set to another, from one vector space to another. So you give it vector, a tensor transforms it to another vector. And that transformation is linear. We will often need to consult the basic definitions to establish the tensor characteristics of any object of concern. The attributes then follow. The attributes follow. We begin here with the inverse of a tensor. What is the inverse of a tensor? The inverse. A tensor may possess an inverse. So if a tensor is a transformation, then the inverse is the inverse transformation. If it does possess an inverse, that tensor is said to be invertible. If it does not possess an inverse, if it's not possible to invert a tensor, when an inverse is impossible, we call that tensor singular. So when we say a tensor is singular, we mean we are unable to find an inverse for it. Or it is not invertible. The identity tensor, which we discussed last week, induces the concept of an inverse of a tensor. Given the fact that T belongs to L, which you should read this as if T is a member of the set of tensors. So if T is a member of the set of tensors and U is a member of the set of vectors, then the mapping W is equal to TU produces a vector, because when you operate T on U, what you get, because it's a linear transformation of vector to vector, it must be a vector. So W must be a vector. Imagine a linear mapping Y, if one exists. Just imagine that one exists, which if it operates on the W we have here, it produces our original argument U. If we can find it, is it possible for us to find a linear mapping Y, which when we operate it on W, it produces the original argument U, such that Y operating on W gives us U, which is our original argument. Remember that W itself is equal to TU. But now, YW is equal to U. As a linear mapping operating on a vector, clearly Y is a tensor. From what we have seen now, Y must be a tensor. And I want you to go to the chat room and tell me, why is it obvious that Y must be a tensor? Let me repeat how we got Y. We first of all started by saying W is equal to TU. If it is possible to find a Y, which is a linear transformation, which when we operate it on W, we get U back. When we operate Y is a linear transformation, we operate it on W, we get U. And I said clearly, Y is a tensor. Why is it obviously so? Please be in the chat room and tell me why Y must be a tensor. Chat room, why is Y a tensor? you say it is because it's the inverse of t. No, that's not why it is obviously a tensor. We don't know. We cannot know. Well, why is the inverse of t? It's a linear transformation on the vector w. Ademola Daramola, you got the answer correct halfway. You got it is linear. Yes, it is a linear transformation on the vector w, but that is not enough to make it a tensor. Why is it obviously a tensor? Why operating on W gives us U, and why is a linear transformation? So I said clearly, why is a tensor? Why is that so? So we said, imagine a linear mapping which is also a linear transformation. Why? If one exists, that operating on W, that is operating on a vector, produces our original argument U, which is also a vector. So it is a linear transformation, it operates on a vector, and it produces a vector. When I now say it is obvious that Y is a tensor, of course, It is a tensor because it is a linear mapping, and it takes a vector and it produces a vector. Why is it obvious? Because it's a linear mapping operating on a vector and producing a vector. So that is what makes it obvious. So obviously, clearly, Y is a tensor. If you can find a linear mapping that will do this work, then it is a tensor. Now, it is called an inverse of T because if you see YW is equal to U, YW is equal to, remember that W itself is TU. W itself is TU. So YW is written as YTU. And we said YW is equal to U, is equal to U. Well, but we know that there is a tensor which when it operates on an argument produces the same argument. That tensor is called the identity tensor. That is that YT is equal to I, the identity mapping or the identity tensor, the identity transformation. For this reason, because YT is equal to I, we say Y is T inverse. So if we can find a Y, which is a linear mapping that does this, it's definitely a tensor, and it is the inverse of T. That's what it is, the inverse of T. The next thing we shall show is that if YT, like we have said there, if YT is equal to I, we want to prove next that TY is equal to I. Now, I want you to go back to the chat room and tell me in transformational language, what is the difference between YT and TY? What is the difference? Or is there any difference between YT and TY? Go to the chat room. If you say there's a difference, tell me what the difference is. Let us go to the chat room and ask ourselves, is there a difference between YT and TY? Pretty. Ademola Daramola says there's no difference. I disagree with you, sir. There is a difference between YT and TY. So I've answered the first part. Is there a difference? There is a difference. So you are now left to tell me what the difference is. Aishat, you are, well, correct, but that's not the answer I'm looking for. Well, there's a difference. They don't give the same result. Judah, I didn't say that. I don't agree with that. Marvelous. I don't say it's not commutative. Who told you it's not commutative? We've not said it's not commutative. You are using big words. We've not even brought that word into play. So, okay, let me type the answer. So far, we do not know whether yt and ty are the same, but we will now prove they are the same. We want to prove they are the same. So to prove they are the same, first of all, you can see that we have no, or initially, we don't know them to be the same. Do you agree that initially, from what I've explained, we don't know them to be the same? Let me just see whether you agree with me or not. Whether you have seen that by my explanation, we were not told that they are the same. Can you see that initially we are not told that they are the same? From that explanation that I've given. Because when we say yt, of course, we know what happens when you operate t on u. We have been told that we will get w. And when you operate y on w, we have been told you are going to get u. But when you operate y on u, we don't know what that will give us. But we are still going to operate t on whatever that gave us. So we don't know what we will get at the end. I've only had one person agreeing that they understand that. So I want a confirmation from others. Is my explanation here that of the difference between ty and yt, is it clear what it is? Can you see that yt and ty are not the same? Okay, because when you have yt operating on a vector, you first of all operate t, and then you operate y. When you have ty, you first of all operate y, then later you operate t. We do not have a proof so far that those two will give the same result. So what we want to do now is to prove that they will give the same result. Okay. To prove that they will get the same result, let us begin here. We say that W is equal to TU. But we said earlier that TY, we said YT is an identity. So if YT is an identity, instead of operating T on U, we can operate I on U first before we operate T, because I, which is YT, will not change anything. So TYT operating on U does not change anything. And TYT operating on U is the same thing as TY operating on W, because TU itself alone is W. So TYT operating on U is the same thing as TY operating on W, which is the same thing as T operating on U or operating on IU. Doesn't matter. These two are the same, whether you operate T on IU or you operate T on U. But the answer at the end of the day is W. So that means that if you operate T on U, you get W. What that means is that if you look at this expression here and the last expression, that is when TY operates on W, it gives you W, which means that TY also is an identity. YT is an identity, TY is also an identity. So if both of them are the identity tensor, that means that both of them are the same. So the first equality is from the definition of W, the second by the fact that YT is equal to I. It's clear that TYW is equal to W, so that TY is equal to YT is equal to the identity as required. Now, some of you thought it was obvious, but I said prove it. Prove the equality. The fact that you think something is equal doesn't mean you can prove it. What you have on this page is the proof that TY is the same thing as YT. You thought it should be the same, but you have to prove it. If you can't prove it, then it's not the same. So now we have proved that if TY is identity, then YT is also identity. So if it means that if It means that if y is the inverse of t, t is also the inverse of y. So they are mutual. The inversion is mutual. Y is the inverse of t, t is also the inverse of y. So we have finished the discussion about the inverse. That is, if an inverse exists, then if that inverse is y, then t itself is the inverse of y is the inverse of t. So we are now going to go to the idea of tensor bases and components. Before I move on, let me state here at this point that every idea we have about tensor has a parallel in vectors. That is one of the reasons why we spent a lot of time explaining the idea of vectors earlier. If you forget or you are confused about anything, just know that there must be some parallel between whatever idea you see in tensor and what you have already known about vectors. Tensors, just like vectors, can be expressed in component form with respect to a system of coordinates created with basis vectors. Using the orthonormal basis, ONB, by ONB I mean orthonormal basis. For a typical tensor T, we can write that T is equal to Tij EI circle times EJ, where the Tij's are scalars and EI circle times EJ or EI, what do we call it now? Dyad, EI dyad EJ is what you know as a dyad. There are 9 scalar components. I hope that is obvious. This can be computed using the indicial notation and the summation convention. Accordingly, we can say T is equal to T11 E1 E1, T12 E1 E2, T13 E1 E3, T21 E2 E1, T22 E2 E2, T23 E3 E2, T31 E3 E1, and T32 E3 E2, and T33 E3 E3. So, unlike your vectors where you have 3 components, there are 9 components when you expand a vector on its basis, because there are 9 bases, because there are 9 possible ways of doing a dyad between the pairwise on the orthonormal basis. There are 9 possibilities. And there is nobody that tells you that E1 circle times E2 is written as E2 circle times E1. We don't know. We don't know that. So nobody said that. So you don't make that assumption unless you can prove it. So as long as you do not prove that E1 dyad E2 is written as E2 dyad E1, notice that if you operate that on a vector, you are going to get different results. So if you operate E1 dyad E2 on a particular vector, operate E2 dyad E1 on a particular vector. But instead of even talking about this in theory, I want you to take a vector V. Take a vector V, go to the chat room, operate E1 dyad E2 on that vector, operate E2 dyad E1 on the same vector, and tell me what the result is. Go to the chat room. I will do it here. Go to the chat room and tell me the result. Operate E1 dyad E2 on V and operate E2 dyad E1 on V, and let us see what the result is. Chat room. Okay, so I am assuming by now that everybody can see that there is nobody that says that E1 diad E2 is equal to E2 diad E1. It's not the same. They may look alike, but they are not the same. Just that reversal changes the diad to something else completely. So we can find these components in terms of the tensor T in a way like so if we now want, so we have 9 things to find. You remember that when we are talking about vectors, we have three unknowns to find. In the case of tensors, we have 9 unknowns to find, and it is easy to find these 9 unknowns just the same way we found for the tensors. So what you are going to do is that you look at this product, E alpha dot Te beta. If you say E alpha dot Te beta, is written as Tij. Okay, let us see. Because if you let me go back one step. So what we are going to do is that we are going to change T to this Tijei circle times Ej. That's what we are going to do. So we have T here. So we are going to turn this one to Tijei circle times Ej. But you know, so that's why we have this, because this Tij is a scalar. That's why we can bring it out. So this E alpha is still here, and dot EI diad EJ, which we have, into E beta. So all we have done on this line is that we have changed T. We have changed T to Tij EI diad EJ. So that is, if that is how we express it. So we can use that to find T. So the next line, we open this dyad. You remember that this dyad is simply Eij dot E beta, sorry, Ej dot E beta, which is delta J beta in the direction of, that's delta J beta in the direction of EI. There's an error here. This will be delta J beta in the direction of EI. I think I made a mistake here. Let me just see what happened here. Okay, so I corrected it in the next line. So I hope everybody can understand what is happening here, because we get delta J beta because Ej dot E beta is delta J beta, and then EI is left as a vector. So, and if you do E alpha dot EI, it gives you delta I alpha. So that is what you have. And if you have delta Ij, delta I alpha, delta J beta, if you can remove this by substituting alpha for I, and you can remove this by substituting J for substituting beta for J. So at the end of the day, this gives you T alpha beta. So E alpha dot Te beta is T alpha beta. I want that to sink in. If you have any problem with the 3 lines, with the 4 equations, tell me which one. 1, 2, 3, 4. There are 4 equalities there. Why is equality 1 correct? Let me just put it as a question. Why is this first equality correct? Because if you know why equality 1 is correct, you can, everything else is clear. Why is the first equality correct? No, 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 no. Aha. iShat is the one that got it. We substituted in T. We substituted an expression for T in that in the expression on the left-hand side. We changed T to this. We substituted for T on the left-hand side. That's all. That's why equality 1 is correct. We just substituted for T. If you understand why equality 1 is correct, so can you tell me why equality 2 is correct? Why is this second equality correct? Why is the second equality correct? Yes, I've seen your answer, Patrick Oloko. Just okay, that we do that. But before we did that, we first of all opened the dyad. We opened the dyad, then we used the chronicle delta as a substitution symbol because we know that ej dot e beta is ej beta. Good. Onyekonsola, you are doing well. More answers, more participants. I hope the class remembers that you are being judged by your participation in the chat room. I hope you remember that because I've said it over and over. So I still, okay, Khalid Ajayi is having a question. Which equality, Khalid, which equality are you discussing? Or which, because there are 4 equalities now. Which equality are you discussing? I'm waiting for Khalid to answer me. You're asking a question. I'm trying to find out what you are referring to, for which equality. EI inequality has disappeared in equality 2. So let me just go and look at EI in equality 1 has disappeared in equality 2. Let me just see what she's talking about. Hey, I said that was an error. I corrected it. Can't you see? Can't you see that I've corrected it? Look on the screen. Can you see my screen? That I've corrected it. EI didn't disappear. It was an error. I've corrected it. Okay, so Khalid, you can see it. Good. Okay. I am taking it that everybody understands what we have done. The first thing is that, let me go back again to explain it. In the first expression, we simply substituted the expression for the expansion of T. The second expression, we did Ej dot E beta to get delta J beta, and every other thing is there. In the third expression, we did E alpha dot EI, which gives us delta I alpha. And lastly, we applied the substitution property of the 2 deltas, and we got T alpha beta. So if that is the case, if that is true, we can therefore say that the Tij is simply ei dot tej. If Ti alpha, so the Tij is simply this. So we can say that T is equal to Tij Ei circle time Ei diode Ej. So the Tij is obtained by doing this. First of all, operate T on Ej and then take it, because that will give us a vector, and take a dot product of that vector with Ei. That is the expression that gives us Tij. So in particular, Ei dot Iej is equal to Ei dot Ej is equal to delta Ij, so that the identity tensor has the representation that I is equal to delta Ij Ei circle times Ej, where it becomes clear that our familiar chronicle deltas are simply the scalar components of the identity tensor. And now, if you, I don't want to rush out of this page 8. I want you to see something that is important. You remember how early we introduced the identity, we introduced the chronicle delta. By the time we introduced the chronicle delta, we didn't know anything about tensors. So we couldn't tell you everything about the chronicle delta. What has transpired now is that the chronicle delta is actually the components of the identity tensor on its basis. That's all. So what the scalar you have been handling are simply the scalar components of the identity tensor. But we couldn't tell you that. The conical data we've been dealing with, we'll be calling substitution symbol, we'll be playing with, we'll be doing one thing or the other with. The true nature of the conical data has come out now. It becomes clear that our familiar chronicle deltas are the scalar components of the identity tensor. You know what the identity tensor is? The identity tensor looks like a trivial thing, but it is not trivial. It plays a lot of roles, and you can see how influential the chronicle deltas have been since, and they are actually the scalar components of the identity tensor, as you can see from here, from this equation. This second equation here shows that the chronicle deltas are the scalar components of the identity tensor. Because if you compare that with the equation for T is equal to Tij Ei circle times Ej. I is equal to delta Ij Ei circle times Ej. So if Tij are the scalar components of T, delta Ij are the scalar components of the identity tensor. So we can break any tensor into its components, even including the identity tensor. Can break any tensor into its components. Before we move on from this page, I want you to tell me the scalar components of the annihilator tensor. Go now and go to the chat room. Tell me the scalar components of the annihilator tensor. You can start from here. What is the scalar component of the annihilator tensor? So if instead of Ei dot Tej, you say Ei dot Oej, what would that be? What are the scalar components of the annihilator tensor? Yes, big O. What are the scalar components? I want more answers. I've seen one. Okay, you got the answer 0, but nobody has got the correct answer of how many the zeros will be. How many zeros will we have? Aishat got the answer right. There are 9 zeros. There are 9 zeros. And David Akinola, 9 zeros. Olayinka, 9 zeros. And for those who don't, for those for whom that is not obvious, let us go back. You remember here, it means that if T is the annihilator tensor, it will be 0 E1 circle times E1 plus 0 E circle times E2 plus 0 E1 circle times E3 plus 0 E2 circle times E1 plus 0 E2 circle times E2 plus 0 E2 circle times E3 plus 0 E3 circle times E1 plus 0 E3 circle times E2 plus 0 E3 circle times E3. If it was the identity tensor, it would be 1 E1 circle times E1 and 0 E2 circle times E2, 0 E1 circle times E3, 0 E2 circle times E1, 1 E2 circle times E2, 0 E2 circle times E3, 0 E3 circle times E1, 0 E3 circle times E2, and 1 E3 circle times E3. So the only things that will survive are when you are the terms with E1, E1, E2, E2, and E3, E3. All the others will vanish. So those are the things. So the identity tensor is simply E1 circle times E1 plus E2 circle times E2 plus E3 circle times E3. That's what the identity tensor is. Whereas the annihilated tensor is just 0 throughout. So I hope that is clear to everybody so that we can move on. So when you are dealing with scalars, if you are dealing with scalars, there is only one way to define product. For scalars, there is only one product. So multiplication, and that product is commutative. So 2 times 3 is written as 3 times 2. And in fact, many times you just say 2, 3. If once you put a space there, we know you are multiplying, because it doesn't matter. If it's a multiplication, you don't even need to remember to put a sign between them. So, but when you come to vectors, we have defined scalar multiplication, so you can multiply a vector with a scalar. We have defined scalar product, where you are multiplying 2 vectors together to get a scalar. That is, you are multiplying them scalarly. There is also vector product, where you are multiplying 2 vectors to get a vector. And then we said there's a tensor product. So there are 4 different ways you can take a product that involves vectors. 4 different ways. Now, if you move to higher order quantities, so from scalar to vector, we have 4 different multiplications. When you get to tensors, the number of different multiplications are up to 16. So don't just begin to examine them. But we are going to be specific. We are going to deal with only 2. It's only 2. The first one we have already dealt with. The first one, we have already dealt with it here. You see, all the places where you have one transformation following another is a composition. When you have ty, t, ty, ti, ty, yt, yt, ty, all those ones, those ones are called, is a product called composition. Okay, so as you move to, we are restricting ourselves to specific products that have practical uses. One of the few that we will consider is called composition, and we've already seen it. So we can only talk about it a little bit more. The composition of 2 tensors produces a tensor of the same order. It is the product with no explicit operator. Some textbooks use the dot, which are declined to use this. The reason, let me just tell you this. The reason why we will not use dot to indicate product between 2 tensors is that anytime you see one dot like that, just be sure that what is on the left-hand side and what's on the right-hand side are both vectors, so that there is no confusion. So a single dot shows that you are multiplying vectors together to get a scalar product. We do not want to imply any other meaning to that thing. So when we have two tensors and we want a composition, we just put the two of them together, just like you have S and T here. Given that S and T are tensors, the sequential operation of the two tensors on a vector produces a vector. The combined effect of the two is the composition product of the two vectors. For instance, STU is written as S operating on the result of TU. STU is the same thing as the result of S operating on the result of TU. If the result of TU is V, then it is written as SV. And if the result of S of V is W, you have all of this. That is if S and T are tensors and U, V, and W are vectors. By the definition of the vector space, it's obvious that V and W are vectors. So hence the composition ST, W is equal to STU. Transform the vector U to vector W. We have just completed the proof that the composition of two tensors is itself a tensor, because the composition of two tensors, because it gives it, when it operates on U, it gives W. And we know it is linear, because if TU is linear and SV is linear, then the combination of them will obviously be linear. It can easily be proved. So the composition of S and T is a tensor itself, and it is which one do you operate first? Is it in S and T? Which transformation comes first? Go to the chat room and tell me which transformation comes first. In ST, which transformation comes first? In the composition ST. Okay, so you can see that it is the tensor on the right that performs its transformation first, and then after that, the one on the left finishes the transformation. So in a composition, the composition begins on the left and goes to the right. So if you have a composition of four tensors, you are going to start from the left and you move to the right. So the composition product is right to left associative. You start on the right and you move to the left. Sorry, you start on the right and you move to the left. Start on the right, move to the left. So it is not the same thing as starting from the right and left and moving to the right. So TS is different from ST unless something happens. Normally, there are two different transformations. ST and TS are not necessarily the same. Now, can we also get the components of a dyad? Components of the composition. Can we get the components of the composition of a dyad? So suppose you have the dyad E alpha, E beta, and the dyad EI, EJ. So if you do the composition of the two operating on U, what do you get? Because we must start on the right. So operating, so you have EJ.U here with EI, and then you now have E beta, EI here, E alpha. So you have these two brackets are scalars. So you can see that if you look at it very well, it's written as E beta dot EI into EI dyad EJ. It is not easy to see the second equality. It's not easy. So what you do is work it backwards. Work this backwards and see that from there back, you get this answer. You can't, if you are finding it difficult to see the second equality, work backwards from the third expression to the second expression. And you will see, you get exactly the same thing. So let me see, please do that, work backwards and tell me if you have succeeded in the chat room. Tell me when you have succeeded in the chat room. Work backwards. Work backwards. Emmanuel Lincoln said he has succeeded. Who else has succeeded? If you don't tell me, I'm assuming you are not obeying the instruction. You are not doing what I told you to do. Because if you have obeyed, you will tell me whether you've succeeded or not. Or you don't understand what I asked you to do. If you don't understand, tell me. I will tell you again. Okay, so David, I hear you. Okay, Fagbemi says, please, sir, come again. Okay, so I'm going to come again. So if you are sleeping, what I'm saying here is that in the first expression here, you open the bracket on the right. If you open the bracket on the right, you see ej.u, which is this, and in direction of ei. That's what you have here. If you now open the bracket on the left, you see e beta dot ei in the direction of e alpha. So that's what you have here. I've said that is equal to the third expression. Now, it is easy to see the first equality, it's easy to see the second equality, but it is not easy to see the third equality. Now, if you want to see it, work backwards, go back from here by just opening this bracket, opening this dyad, you should get this expression. So what I want from the person who asked the question is, if you open this bracket, can you get the expression before it? If you can, then you are succeeded. So let's just see. I'm now asking Mr. Fagbemi, Mr. Come again. So I want to see whether you can do it. I'm waiting for Fagbemi. I'm looking for Fagbemi. Fagbemi, you're in trouble. I'm looking for you, just you. I'm waiting for you. And I'm not moving until Fagbemi answers me. Aha! So Fagbemi, I got you. So you can see. So that's the thing. So you have to try. So if you try, you see what I am saying. So let me make the conclusion before I release us to go on break. Let me just go back again. So it shows one result. If you want to compose two dyads, there is a trick. You don't need to work out all of these things. You just take make a dyad out of the first vector and the last vector and do dot product in the ones that are in the middle. It doesn't matter. Even when you have very many dyads, if you have very many dyads and you want to compose all of them, all you need to do is to take the very first one and take the very last one and then do dot product on all the ones that are near each other. That's the answer. So the composition of a chain of dyads follows a very simple rule. You take the very first one, you take the very last one, and you make a dyad out of the two. Every other thing, you just take dot products of like AI2, AI3, AI4, AI5, all of them. So that is the answer you get here. Reducing any tensor, so it can be shown that the result is simply taking the first and the last of the vector operands and multiplying it by the scalar products of all adjacent vectors. So we are going to go on a 15 minutes break. So we are back at 11:16. We are back into class at 11:16. 11:16, 11:16. We will talk again. Okay, we are back to slide 12. We passed it to just give a result on slide 13. And let us see what happens here. If we want to look at the components of the product, of the composition product, we want to see what are the components of ST. Well, T, we remember that T is TIJEI diad EJ. Similarly, we can say S is S alpha beta E alpha diad E beta. You know, we cannot use I and J again because I and J are already used twice here. So that's why we used the other symbols. Again, remember that S and T's are scalars. So you can put all of them, you can pack them away. You cannot move the vectors as you like, but you can move the scalars as you like. I want to go to the chat room. Why is it possible for us to move the scalars as we like? Like I can move Tij here, but I cannot just move the vectors anyhow. Why? Why must I be careful how I move the vectors? Whereas I can just move this. Once I know something is a scalar, I can move it. I want you to go to the chat room and tell me why. Why is it okay? I will type the question. Type the question here. Okay, so I have I've written the reason why you can move scalars at will, but you cannot move vectors at will in an expression. You must always remember the relative positions, especially with the symbols. They don't just move back and forth. And it is coming from commutativity and lack of it. Okay, so that we know, so we can move on. Okay, so where do we go from here? So here, if you have this expression, you know where we are using alpha and beta and I and j here. So if you pack all the scalars to one side, you now have this diode operating on a diode. And you remember that if you want the final result of this diode is E alpha diode EJ, which is what you have here, and then the ones that are near each other, they are dot product. So this dot product will give you delta beta I, and then when you now operate delta beta I, you can see that you have S alpha I Tij E alpha circle times Ej, which you can write as Sik Tkj Ei circle times Ej. The result of the product of two diodes in this section can be generalized to a larger number of diodes. So this is what, so if you want to find the components of a composition, this is how you find it, and this is the component of a composition. So you have Sik Tkj Ei circle times. So the first index there is Ei, and the second index is Ej. The other thing remaining is just a dummy between the variables, so no problem with that. So we've already expressed this result. So we don't need to worry about that again. You know that result, and you use that result. So we get to 14 now, page 14, where we discuss the transpose. The transpose of two, if you are used to matrix algebra, you know what a transpose is. And the transpose we define here does not look the same, but by the time you finally understand it deeply, you will see it is the same. It doesn't look like it, but this is a more fundamental definition of transpose when it comes to tensors. So you will see later that you can derive that transpose you are doing in your linear algebra. You can derive it from here. This is a more fundamental definition. Given any two vectors u and v and tensors s and t, S is called the transpose of T if U dot SV is same thing as V dot TU. That is, if you do the composition of the vector in reverse order, that is, first of all, operate it on one and then do the dot product on the other one, and you just reverse the order. If the answer you get is the same, then those two tensors are transposes of each other, because all you need to do to get the other one, for two vectors, just reverse the order, you get the answer you got before. It is customary to use the same symbols for a tensor and its transpose. Accordingly, the transpose of S will be written as S transpose. Furthermore, by virtue of definition of transpose here, if S is transpose of T, then T is the transpose of S. It can be proved easily in a single line, because since U and V are any two vectors, just let U be V and V be U, and you get that if S is transpose of T, then T is the transpose of U. So the definition of transpose then tells us something about the idea of symmetry. A tensor equal to its transpose is said to be symmetrical. Tensor S is symmetrical if S and the transpose of S are the same. So when a tensor and its transpose are symmetrical, then we say that the tensor, and when the tensor and its transpose are the same, then we say the tensor is symmetrical. Now, when you are dealing with vectors, you can have a vector, you can put it in terms of its components if you want, usually three in a three-dimensional space. But if you know two scalars, you already know everything about a vector. And those scalars are what? What are the two scalars that you need to know? And once you know them, you know everything you need to know about a vector. Go to the chat room and tell me what scalars are characteristic of a vector. What are the scalars? What scalars? There are scalar values you need to know about the vector. Two of them. Is this class awake? Let me. Magnitude and direction. That's it. Magnitude and direction. When you know the magnitude and direction, you actually know everything you need to know about the vector. You know its magnitude and you know its direction. So, good. So, same thing with a tensor. It turns out that in practical uses of a tensor, especially in design, there are three scalar quantities that are especially characteristic of a tensor. For this reason, some textbooks call them characteristic values. I've said, tell me the two scalars that define a vector. You've already done that. So let us look at the characteristic values of a tensor are called the principal invariants. These principal invariants, they are scalars. There are three scalars. Once you know those three scalars, you know the principal invariants of a tensor, and basically you know that you know all you really need to know about the tensor. And they are called number one, number two, and number three. We could say the first invariant, the second invariant, and the third invariant. The first invariant is this. This is how you compute it. This is how you calculate the first invariant. You take any three linear independent vectors, any three. It doesn't matter what they are, as long as they are three linearly independent. What you do is take the scalar triple product. The scalar triple product, we write it in this bracket form. It simply means A dot B cross C or A cross B dot C. You know the two are equal. So you just take this bracket, which is the scalar triple product of the three linearly independent vectors. It doesn't matter what they are, as long as they are linearly independent. So the first principal invariant, the way you do it is that in the first bracket, you transform the tensor, you transform the first vector, then you transform the second vector, and then you transform the third vector. In each case, computing the resulting scalar triple product. When you do that and you divide the sum by the scalar triple product of the three vectors, you get a quantity called the trace of the tensor. That trace is the first principal invariant. That trace will give you the same value no matter what vectors A, B, and C you choose. It doesn't change. It doesn't matter what vectors A, B, and C you choose. Just the same way that you can get the magnitude of a vector no matter what coordinate system you are in. You are still going to get the same magnitude. So that is the thing. So that is the trace of the vector. That is the fundamental definition. When you go to textbooks, you will see any other definition you see. You can compute that definition from this one. This is the fundamental definition of the trace of T, which is the first principal invariant. It is called the trace. The trace of the tensor is number one. The second invariant is very similar. Instead of transforming one of the three vectors, you transform them two by two. The first one you transform A and B, the second one you transform B and C, and the third one you transform C and A in the same way, and you divide again by the triple product of the three vectors. Any three vectors, any three linearly independent vectors. If you do that, you get the second principal invariant, which is the trace of the cofactor of the tensor. We will talk about cofactors later, but don't worry about what the second equality means. This is the computation formula for the second principal invariant. But you will see later that it is the trace of the cofactor of the tensor. The third principal invariant is you transform, before you take the scalar triple product up, you transform every one. And there's only one way to transform all the three. So there's no addition, nothing. So TA, TB, TC are put together in a scalar triple product like this. And when you divide that by the scalar theory product of the original vectors themselves, you get a quantity called the determinant of the tensor. And that determinant is the third principal invariant. Once you know these three, you basically know what is important for you to know about the tensor. And they are called the principal invariants. These are the three principal invariants. The first one is the trace of the tensor. The second one is the trace of its cofactor. And the third one is the determinant of the tensor. Again, you will see definitions of determinant different from this. But this is the fundamental definition. The other definitions you see can be derived when you know this one. So I'm going to project from here. So let us go to slide 19. Forget about slide 18 for now. We go to slide 19. And we are now trying to say, okay, what is the determinant of a product? What is it? So if I do a composition of tensors A and B, I want to show that the determinant of A and B is written as the determinant of A times the determinant of B. The multiplication sign there is ordinary because the determinant of A is a scalar, the determinant of B is a scalar, and there is only one way to multiply two scalars. So that's types. It is not a dot product, it's not a vector product, it's not a tensor product, it's just product only. So now, we want to prove this on this page. We are proving this expression on this page. So to prove the expression, select any three linearly independent vectors A, B, and C. If B is not singular, that is, if it is invertible, we can easily show that if A, B, and C are linearly independent, then U, which is equal to BA, V, which is equal to BB, and W, which is equal to BC, are also linearly dependent. In fact, that proof is in the book. It's in question 2.25. So that is, if A, B, and C are linearly dependent, and B is not singular, then U, V, and W are also linearly independent. For proof, go to question 2.25 in the book. So I don't want to spend time to do that here. So let us therefore write the expression for the determinant of AB. Determinant of AB is AB A, AB B, AB C divided by ABC. So you take the product, operate it on A. You know, you first of all operate B, then operate A. Then you operate B, then operate A. Then you operate B, operate A. So that is what you get as ABA, ABB, and ABC. And then you divide it by the triple product of A, B, and C. If you do that, you have got the determinant of A. But because what you have up and what you have down are both scalars, what you have up is a scalar, what you have down is a scalar. It is possible for us to write this expression. We can have ABA, ABB, ABC divided by BA, BB, and BC, which is also a scalar. So we can also put it up here because this can cancel this out. Don't forget that what we have in the square brackets are all scalar. The result is a scalar. So we can cross this out with this, and we get back our original expression. But we have said U, we have defined U as BA, and V as BB, and W as BC, and we said U, V, and W are also linearly independent. If that is the case, we can write what we have here as AU, AV, and AW. We have these three, AU, AV, and AW. And we have divided it by BA, BB, and BC, which is U, V, and W. So what we have now here, BA, BB, and BC over ABC. So if you look at this very well, you will see that since U, V, and W are linearly independent, this first expression is the determinant of A, because we said you can choose any three linearly independent vectors and you form this product. Similarly, BA, BB, and BC over ABC is the determinant of B. So we have proved that the determinant of the composition is the product of the determinant of each of the tensors in the composition. So that is the proof of that, as we have decided to do. So that is there. So We now want to talk about the inner product of tensors. I'm going to do something about the two tensors. What you can do is take the transpose of one and take the transpose of one and do its composition with the other one. If you take the trace of the resulting tensor, what you have is the inner product of the two tensors. And it doesn't matter. You can either take the transpose of the first one or take the transpose of the second one. But you maintain that. So if you take the transpose of the first one or take the transpose of the second one, the other you will discover later on, the other is completely irrelevant. You have what is called the inner product, which is also a scalar product of the two tensors. Because what you get at the end of the day, because it's a trace. Remember, by definition, a trace, you can see that a trace is a scalar. So because what you get at the end of this is trace, so it's a scalar you get. So when you, and there you say S dot dot T. So when you do the scalar product of vectors, it's a single dot. When you do the scalar product of tensors, it's a double dot to show the second order power of the tensor. So both of them are scalar products, but it's a scalar product of a higher order. The vector is a single order, so that's why it has a single dot. Scalars are zero order, that's why there's no dot. Tensors are two dots. And so we can now go and find the trace of these two tensors here. So we take the trace of T. Let us take T. Is T. We do we do the reversal of a dyad. When you reverse the dyad, you have taken the transpose of the dyad. It is easily shown that the transpose of a dyad is the reversal of the dyad. So if you take the trace here, you see that it is the trace of T alpha beta. So you take T, you express T in alpha beta, E beta, and then you do this. So when you open that thing, you see that it is E beta EJ is delta beta J, and you have E alpha EJ. Yeah. So if you open up, if you get it here, and then the trace of, so everything here inside the bracket is a scalar except this. The trace of E alpha, the trace of a dyad. I don't think we've established that the trace of a dyad is simply change the circle times there to dot. And because we've not expressed that, I'm just wondering whether we shouldn't stop it here. Let me just see. From the above definition, the scalar component of the dyad basis is given by this quantity. Let's us see. I will want to stop the lecture here because there is something I didn't do, which is to tell you what the trace of a dyad is. I don't think we've done that, and it is an omission. I want us to be able to move from here to here, but then we have not proved that the trace of this dyad is simply delta alpha I. And since that is not proved, we cannot reach the conclusion that we cannot move from here to here. So what I will do, I will stop at page, I will stop here, I will pause here at page 20. I think you got enough for the day. We will start with another slide next lecture, and that slide will show us that the trace of a dyad is simply when you change what you have there to a dot. If you change the dyad symbol to a dot, what you got is the trace of that dyad. And that wasn't established before this point. Therefore, we cannot take this conclusion. So what I will do now is that I'm going to go to the chat room, and I want to to attend to answer any questions you may have had up till now. And if you have, I'll give you 5 minutes to ask me a question. If you have any question, I will answer it. If you don't have questions, we will close the class for the day. So there are questions there for you. If you have questions for me, let me have them. And I want to know whether you have started going to the self-test platform. If you have, are there any questions on that? If you haven't, it is time to start doing that. And before you go to the self-test platform, get a copy of the book down and go through the solved problems in the book before you go to the test platform, because the same questions that will be put to you in the test platform. Admin, has any student come to the test platform yet?
Yes, sir.
Okay, that's admin. Okay, good. So some students have been coming. So please check, do the Q&A first before you go to the test platform. That will make you get better grades there. Because we just want to be sure that you are following that's the way you know you are following the classes. Well, apparently we don't have any questions. So admin, you can shut down the meeting.